So, welcome back students. We are basically discussing a combination of starting material, functional group and transformation based strategies for small molecular target molecules. And in the last lecture we talked about a mechanism based approaches, like we discussed Payne rearrangement as well as Baeyer-Villiger based oxidation and its application. Now, today I will be trying to give you similar kind of mechanism based strategies, which are basically, if you are quite sure about the mechanism of a key transformation, that will help you to design some retro pathway. The problem which was given now is a small molecule, is a cyclopentenone structure, and the target molecule is basically this one, is alpha beta unsaturated carbonyl compound which is having a cyclopentene core structure. Now, starting material initially I am giving it to you for your thinking independently. Starting material which was given, let us say toluic acid, metatoluic acid, starting material. Now, as you can see, basically the target molecule is not aromatic, but the starting material is aromatic. So, basically you need to think about a dearomatization reaction, and you all know the dearomatization reaction which is widely explored, named as Bach reduction. We have explained Bach reduction in terms of its mechanism and how different kind of substituted aromatic group with electron releasing and with electron withdrawing, that will give you two different regioisomeric product in the Bach reduction. Now, here if you do the retro, as it is a alpha beta unsaturated compound, probably the best retro will be the simple aldol dehydration, which we discussed many times. We say if you have a compound something like this, which will undergo a simple 1,2 beta elimination, a beta elimination of a water molecule, which is basically nothing, a aldol dehydration. Okay. Now, you try to draw the parent diketone compound which will undergoing this aldol reaction. So, you say if you having a compound, you put CH2, 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 3 CH2 will be there, CH2, 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 then methyl, and then we say that this particular this particular compound, you will be trying to have this anion which will be reacting here. Okay. Now, we will be coming to this things little bit later on. You will find that there are other anions, like this anion is very extremely acidic, because it is linked with CO2 and CHO, but in reality ketone form will come to it little bit later on. Now, see how this entire diketone was visualized. Now, this diketone, if you now see, this diketone can easily be made through a ozonolysis kind of ozonolysis or oxidative cleavage from this cyclohexene derivative. So, you need 1, 2, 3, 4, 5, 6 this dicarbonyl compound. So, this is CO2, CHO, CH2, CH2, CH2. So, these 3 methylene will be here. So, it is a oxidative cleavage or ozonolysis. Now, see, we are almost close for this Bach reduction partner. Now, if this compound also can be synthesized from this compound. Now, what we need to do? You basically need to do a regioselective hydrogenation at this double bond of this compound to access this. Basically, need a regioselective hydrogenation. Now, last class we have discussed that if you have a homogeneous catalyst like Wilkinson's catalyst, which is basically triphenyl phosphine rhodium chloride, and you do a hydrogenation based on this catalyst, as this is a very bulky catalyst, this will always try to ensure the sterically less hindered olefin is reduced faster. and you can control the reduction. Now, this particular starting material will be easily coming from this toluate ester, which you can easily prepare from this toluic acid as a starting material. So, we have basically disconnected the molecule through a couple of interesting transformation, and also if you are quite sure about the Barch reduction mechanism, then you can predict this pathway. So, now the forward pathway, we will go to the forward pathway now. This toluic acid, first you do a esterification reaction, ETOH concentrated sulfuric acid, you esterified the molecule to give the corresponding ethyl toluate. Then do the Barch reduction with sodium, liquid ammonia, that, and now here I say this is a mechanism based strategy to keep in mind that you always get this regioisomer. You never get this regioisomer in the Barch reduction if you having a electron withdrawing group here. So, that is the most important thing here. Now, I say you do a hydrogenation with a Wilkinson catalyst that will give you the hydrogenation at sterically less hindered olefin site, and you are here. Now, do the ozonolysis which was earlier devised for this retro, then you will find that you basically get CO2 CHO and then CH2 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 your these things and these things. Now, I say there will be possibilities if you treat this compound with base. This hydrogen seems to be mostly acidic, and if this hydrogen reacts, it will also get a compound what will find the CO2VT and CHO reacts, and you basically get, you can get this kind of aldol also. Okay. This kind of aldol, it's in principle is possible, because this hydrogen is much more kinetically acidity. So, in kinetic controlled condition you might get this aldol, but I say our product is something different. You have to have a alpha beta unsaturated aldehyde. So, probably if this aldol undergoes elimination, you can have elimination here or elimination here, but you never get elimination here because there is no beta hydrogen. So, alpha beta unsaturated aldehyde from this aldol you can never make. Now, think about other condition which is thermodynamically controlled, because now this enolate is thermodynamically more stable because having extra methyl group here, extra alkyl group here. So, means that you allow the compound to react with base for more time, So, more time basically will give you the thermodynamically controlled enolate, and then this hydrogen will be abstracted and will react to this aldehyde, and then we can get this particular aldol which is required for us. Now, see, you can easily do the beta elimination and you can now get the desired compound as we earlier discussed. Now, what are the eventually the take home messages? The take home message is basically we are saying that if you having a clear cut idea about the mechanism of Barch reduction, then you can predict which regioisomer is forming, and then mechanism of aldol reaction, mechanism of aldol dehydration. So, we said aldol dehydration there are two possibilities, kinetically controlled product and thermodynamically controlled product. But if you try to allow a kinetically controlled product, you will not get the desired product in this case. Now, if you allow thermodynamically controlled product, means that you allow the starting material to generate the thermodynamically more stable enol, you get the desired product. So, if you have a clear cut concept about the mechanism of the aldol dehydration, then you will be able to do this transformation. And then finally, we are talking about a Wilkinson catalyst, which is a sterically bulky catalyst and fix or will undergo hydrogenation at sterically less hindered olefin. Sterically less hindered olefin will be hydrogenated. Let us say for this particular case, you are having CO2 here, methyl here. So, there are two hydrogenation site, this or this is sterically less hindered. So, this will be hydrogenated with this catalyst and basically you will get CO2 ET and this double bond. Now, this double bond will be doing the oxidative cleavage. Basically, a combination of a reaction which will help you to design the entire pathway in a very efficient manner. The next problem which we will be now discussing, it is an interesting one, but here the mechanism we have already discussed, same like Barch reduction. So, you will not focus about the mechanism much, we will say that how this reaction was visualized. A target molecule is this, and I say this target molecule can be accessed to this starting material with this CH3CO, CH2, CO2 ET, right. And actually this seems to be simple, If you see this target, you can basically visualize the target might be achieved from something like this compound. Like if you have this olefin and ketone, you can do a FGI through MCPBA based. As I say, MCPBA will also have the possibility to undergo or to make this Baeyer-Villiger reaction possible. So, probably this ketone you need to protect it. So, this ketone needs to be protected, PG. Let us first formulate the disconnection, then we will come to the forward synthesis. Now, here the starting material is given ethyl acetoacetate, that is a very simple starting material, and ethyl acetoacetate you all know, if you treat one equivalent of base, it basically gives you this carbon ion, because this is highly kinetic acidic, this hydrogen is extremely acidic. So, one equivalent of base will give you this. Now, we will now formulate that this part and this part is your starting material, the double bond CH2X, CH2X. So, now what we are visualizing, we say we put this CO2 ET here and then we do the disconnection. Okay. So, this now looks absolutely perfect. What you need to do? You basically need to remove this dicarboxylate ester by simple acid hydrolysis or basic hydrolysis and decarboxylation. These are basically beta keto ester. So, after hydrolysis this will give you beta keto acid. So, now we are almost close. So, you can basically try to get this with a minus with a double bond CH2X with a double bond CH2X Yes. So, we say this minus and this minus will react in a normal alkylation mode, and basically you can get this target, but in route we have to make sure the proper care of the stereochemistry has been taken care, sorry not stereochemistry, is basically proper care of this this protecting group. So, this protecting group you need to be very careful. Now, start with this ethyl acetoacetate. Said you generate this anion by simple base. So, we are doing it. Now, 2 equivalent, if you use this compound as a 2 equivalent and we use this bromo, we are seeing that this compound 2 equivalent and this compound 1 equivalent, because this compound is having 2 electrophilic site. This compound is having 1 here and the another will be this site. This some control is essential, and then you can basically have this alkylation to give you the compound which you are looking for, CH2 okay. Now, here I said okay, you first do this decarboxylation here, you just do the basic hydrolysis and heat it. So, 2 equivalent of carbon dioxide will release and then will give you the product this. So, here these things will be hydrolyzed, will give you carbon dioxide gas, will give you carbon dioxide gas. So, now you are here, you can in principle directly use MCPBA, but see there are ketones here. So, that might undergo bioradical oxidation. So, a protection group might help you. So, how do you protect it? You treat with ethylene glycol and simple H plus. This compound will be now protected as its double bond will remain similar, CH2 CH2 yes. So, now take this compound, as it is, now draw this compound again by keeping other structural element as same. Actually, the other oxygen we did not protect here. So, if you can think it, this also needs to be protected. Okay, this also needs to be protected. So, fine. Now, you do the MCPBA based reaction. So, MCPBA will give the epoxide here and then you treat with simple mild acid, sulfonic acid, to remove the ketal functionality, and that will now give you the target molecule which was desired. Now, there are other ways to do this synthesis also. So, this target which was initially given like this particular target, I am not going to explain that strategy, but I will give you a clue. This compound also can be synthesized by using this ethyl acetoacetate as well as this corresponding bromide by enamine alkylation. Enamine alkylation also you can use it. but the process which we have just shown is very simple and is technically absolutely no issue. You can control the chemoselectivity by just protecting the carbonyl functionality in presence of the olefin, then you do the epoxidation on the olefin. So, similar kind of problems are always there, and basically you will find that next problem which we will be now discussing is a very interesting problem. Here you need to think about little bit about the stereochemistry. This part is important, as I said, the compound which was given to you having a hydrocarbon unit, this is basically two 6 member rings are fused, and you have a methyl transfusion, this methyl is up, this methyl is down. The target molecule which was this one, the starting material which was given here. Now, we will see the starting material how you can correlate with this target molecule. There is a hydroxy group is there. Okay. Now, basically from hydroxy group you are creating a olefin center. Initially you can think that okay, simple elimination might be possible. Definitely simple elimination is absolutely no issue, you can do it, but now what I will try to do, I will draw the stereochemistry of the given molecule. The cyclohexane chair form here, and the I am drawing the stereochemistry of this starting material actually, cyclohexane chair form, cyclohexane chair form. Now, this is methyl is up, this methyl is down, this is basically a transdecaline, means this cyclohexane equatorial, equatorial gives you a trans. Now, this methyl and this methyl is cis. So, this methyl is axial. So, this methyl has to be equatorial, okay. And this methyl and OH are now cis. So, this OH has to be also axial. So, the drawing is pretty important in the 3 dimensional form. And then now you see that how probably a elimination always takes part if you just simply heat this compound through a water elimination, that is always possible, always possible. But this particular example was taken from a NET exam, which is a Council of Scientific and Industrial Research, who basically gives the fellowship, is called also CSR exam, which gives you a nice fellowship if you want to do JRF or SRF after your MSc program. Like if you want to do PhD, this is a one of the good exam you have to qualify. Now, particular this case, the reagents was given. They have given carbon disulfide, sodium hydride and methyl iodide, and heat is there. Now, this particular reagent is giving, does this reagent sequences is giving you some hint? If you remember Barton-McCombie reaction, we have similar kind of reagents we talked about. Now, what exactly is this? ROH plus C double bond S, and methyl iodide. Now, what is happening? This comes here, goes, and then you basically get a xanthate ester, C double bond S, S minus. This S minus reacts with this methyl iodide to give you this methyl xanthate SMe. And in Barton deoxygenation reaction, Barton-McCombie, we now shine light with the presence of a radical initiator Bu3SNH EIBN to keep this heterotic cleavage, you basically get the hydrocarbon. Now, this particular reaction is named as Chugayev elimination or Chugayev elimination. The Russian scientist Chugayev, who first take this xanthate ester, he first. So, initially if you take the starting material which was given in the earlier slide, you basically have this methyl, and then another methyl is here, and basically you will be having this xanthate ester SME. If this is heated under strong heating condition, you will get the elimination product which was the target molecule. Now, I will draw the 3-dimensional picture. This methyl, this methyl is here, we are having this hydrogen below, these hydrogens are definitely there, and then you are having this OC double bond S and this SME. Now, the mechanism which was proposed by this fellow Chugayev, he said that this elimination is basically a scene elimination. Normally, we always talked about anti-elimination, that hydrogen and the leaving group has to be anti-peripheral arrangement, but this is an example where scene elimination takes place. Now, if you closely analyze, the mechanism basically goes through this way. This sulphide is basically abstract this hydrogen, and this comes here, and this basically knocks down the entire thing. So, in this way this reaction takes place, and this is basically has to be go through a scene elimination. It is sometimes called as scene pyrolytic elimination. Scene pyrolytic means you are supplying enough heat. So, now if you see, if this reaction goes, means that the geometry of this alcohol and the hydrogen has to be cis, axial, equatorial is cis. There is no other hydrogen which is cis with this alcohol. This hydrogen is trans, this hydrogen is trans. So, now after the elimination, basically the product will be formed which you have explained just now. This methyl remains here, this methyl remains here, this other methyl will be also things, and the OH will be just eliminated. So, now if you are not quite sure about the stereochemistry, then also you can able to do it. You just remember that this elimination normally goes through a scene elimination. Now, if you say, you may say that, sir, why we have to study the Chugayev elimination? Probably there are other ways you can do it, but if in the exam they give you the reagent sequences that this alcohol is subjected to or reacted with this set of reagent, carbon disulfide, sodium hydride and methyl iodide, and it is heated. Now, if you know the particular mechanism of this reaction, you can easily formulate how this Chugayev elimination or scene elimination takes place, and finally, the olefin will be basically generating. So, this kind of mechanism based reaction is very important, and that will give you a clear cut idea how different mechanisms are basically controlling the pathway of several reactions. So, if you study a particular transformation, initially try to feel the mechanism, try to get the inner chemical logic of the mechanism, and that inner chemical logic of the mechanism will basically then guide you that how a retrosynthetic problem can be visualized. So, normally this kind of mechanism based approaches are basically closely associated with transformation based approach. Transformation is what? Basically a single step transformation where one functional group is converted to another functional group, but in between there are certain chemical steps which are basically we called mechanism. That mechanism, if you are quite familiar, if you are having sound knowledge of the mechanism, then basically you can think that okay, if this mechanism goes through this way, this product might be obtained. So, like there are few examples we talked about in the mechanism based approaches, we will be talking about some more examples. Till then, goodbye, have a good time.